That's okay.
Okay, I will try to follow you.
Well, hopefully you should be able to follow. Okay, well, we should start, no? I'm just going to talk to you. Right? So, this week's all about correlation and regression, and regression is usually over time series kind of analysis to try and understand a trend, and that's often the correlation between two variables. Right? So correlation is something that you would have done a long time ago, probably, and regression analysis, there's loads of different types of it. But this all links back to pretty much the last half of the semester. So we were looking at experimental design. So the other half of the experimental design is correlational experiments. So you're looking to see if there are actual statistical correlations between the variables, and then how do you describe them. And part of that would then be looking at the trend and how can you describe that trend, and is it possible to forecast it into the future. The other part that's quite, alright. Right, the keyboard stops working. Everything stops working. Okay, this should. Cool. So also we were talking about parametric and non-parametric tests. So parametric tests are when the variables that you're looking at have a normal distribution, they're expected, and there's certain characteristics of it. So every time we do some of those statistical tests, we check for those characteristics to make sure we're allowed to do them. Same happens with correlation. So we've got these two different, these are the kind of most common correlation coefficient calculations, the formula. One's called Pearson and the other one's called Spearman, by the names of the people who invented them. Pearson's assumes that you have pretty much normal distribution, that the characteristics of the variables themselves are meet the certain criteria, and if they don't, then you have to use this non-parametric test. Regression analysis, as I said, it's basically looking to fit a trend curve or line. Linear regression is the first, most basic one, where you put basically a line into your across your data to see where it's going to go. And the curves are kind of more complex regression analysis to try and understand that complexity of the data. And then that kind of moves into time series analysis. So today we'll look a bit at a simple regression. So linear models, as a few, we'll look at some non-linear ones, and we'll perform some of this in the tutorial, and some simple time series analysis. And of course, the reasons is to understand correlation and regression, what are the issues with it, and some basic ideas and issues in time series analysis. You have one more person. So correlation is basically, are X and Y related? Hi, welcome. So where we have something like this, you have these points up the screen, you've got x across one axis and y on the other. This shows there's a really clear relationship between these two variables. As one increases, the other increases. More likely, we'll get some data like this, where there's a bit of scatter, some differences in the data, but there's still a trend that can be seen. So, yeah, in the first one, it's clearly pretty obvious, but in the second one, there is a slight trend. As you increase one number, the other increases, but there's this scatter around the variable. But when we calculate the correlation coefficient, that's basically what is that relationship between the two, and this is a number between 1 and -1, and if it's 1, if it's perfectly 1, then it's perfectly correlated like this. One increases, the other increases at the same speed. If this is kind of, medium correlation to show that there's a positive correlation where one increases, the other increases. And if we go to the negative side, it's basically one variable increases while one decreases. We'll see a bit of this. Something like this is more, pretty much there's no correlation at all. There's just a load of dots on our scatter plot, and yes, often we can find some random correlation potentially, but we might have to dig deeper into the data to see some subsets. And I'll look a bit into how we can do that. But Pearson's correlation coefficient, that's the most widely used. It assumes variables are normally distributed, so it's the parametric test that we have. So this is the parametric version of a correlation coefficient. It can handle some outliers, and it's basically intending to measure, is there a linear correlation between these two variables? And as I said before, one means perfect, -1 means a perfectly negative correlation. So this looks something like this. If we have our little scatter plots, over there would show a positive 1, perfectly straight line, -1 would be perfectly straight line in the other direction, and 0 would be something like this in the middle. And then we've got these kind of slight variance. You can see a slight correlation in that 0.4, but 0.8 is much more obvious. So it's basically, how well do these two variables relate to each other? Can we see an effect of one variable over the other? These perfectly correlating values don't have to necessarily be perfectly on an angle like this. They could be more like this, just saying that one increases at the same speed as the other, and apart from in the middle, it's a bit of an odd one. But usually it looks something like this, where we have pretty much a straight line on an angle. We also have lots of kind of fun variance on correlation scatter plots where there's no correlation at all, but they create these random patterns. So there's lots of kind of fun experiments where you can see what's the correlation between these two variables, and you can create these kind of interesting shapes from your scatter plot. So basically it's calculated like this. Yes, okay, it's useful to have the equation, but most of the time we just calculate it using Excel or R. But this is basically the covariance of these two divided by the standard deviation, or the sum of the standard deviation. So, yeah, we always have to know that this is the calculation, but this is for the population. So this one of the differences with Pearson's is that we talk about the correlation coefficient for the population, but we also talk about R, which is the calculation for a sample. So it's slightly different due to the fact we don't know a few things, but most of the time we're talking about R, because most of the time we're talking about a sample. I don't think I've ever calculated a population one.
So not about rho, but we're talking about small r.
Yes.
So this is what's the difference between the pure correlation of the sample and the population?
It's just a slightly different calculation based on based on the fact that we So x and y here are random variables, and they've got its expected values, but in our sample, we have values already calculated. So we have our outcome. So we use... Yeah, so it's a very slight difference here, but most of the time you're using sample. So x and y are continuous measures. We're looking to see how they relate. We hopefully don't have any outliers. They're normally distributed, and there's some linear. Did I say earlier they can handle outliers? I meant they can't. It doesn't handle outliers very well. But here we're hoping for pretty normal distribution and not too many outliers, and that's why we use Pearson's, as it's a parametric test. If we have some of these assumptions we don't meet, then we use the non-parametric test alternative.
The alternative will be the Spearman rank.
Yes, Spearman's rank, and it basically does exactly the same thing, but you rank the two values first. So you're looking at the Pearson's correlation of the ranked variables rather than the original raw variables. So it's very similar to calculate, but you just have to rank the variables first. That's usually when we have outliers or the very skewed variable distribution, or the irregular variance. So slight variation. It determines the strength and direction of the relationship between the variables rather than the linear relationship. So it looks to see is it negative, positive, and that strength of the relationship. So it's a slightly different variation. And when you calculate the same, so if you have your two variables and you calculate Pearson's on them and you calculate Spearman's, they're going to be slightly different. So you just have to make sure that you know what those assumptions are, and you're using the relevant one for your particular data. So with the ranking, this is the original data. We have something like IQ and hours spent in television. Because of the fact that this is ratios, I expect. It's not necessarily normal. You just rank the data and then calculate the coefficient based on the ranks. This is what I meant earlier. So here we have a very slightly different value based on which one we use, because it's not assuming that relationship's linear. And here it's actually not too bad, because it's actually very similar. Yeah, that's because here we have the data is normally distributed and there aren't any outliers. So it calculates pretty much the same when it's meeting these assumptions. If there are some outliers, Spearman's is less sensitive to these. So it can see that that's quite a strong relationship, and it can understand that those are outliers, whereas Pearson's doesn't necessarily incorporate that into its calculation. If there's no relationship, I mean, if you have an increase and a decrease at the same time, there's no point in calculating this, because you're going to get basically a zero. You can subset your data, or just plot it and describe it, and where here it doesn't really make any sense to talk about correlation. So when we're talking about correlation, just like in all other statistics, we have to describe it in the right way. So we talk about direction, we talk about strength, and we talk about shape. So direction would be positive and negative. How strong it is depends on how high the value is, and really how clear that relationship is. So this is pretty strong. They're all like plus minus 9.9, 0.99. This one here is actually quite a high correlation, but it's still relatively weak when you look at it. This one, there isn't really a correlation at all. Or it says 0.3, Okay, there's a correlation, but it's not really very clear. And then we have these shapes where you can see quite different linear or curved, curvy linear. Not sure how you actually pronounce it, but yes, it's basically how do you describe the how do you describe those shapes? And when you're talking about two variables being correlated, usually we talk about being strongly or weakly or correlated in positive and negative. So, yeah, basically they both look at providing a measure of correlation between two numerical variables. We measure this, the degree of the variable, the measure itself looks at is that variable increasing or decreasing at the same speed, and how can we actually describe that as a value. Pearson's has more assumptions, but it's more popular, partly because it's a parametric test. So actually, most of our variables that we tend to look at, numerical variables that probably have a normal distribution, and the outliers it depends on. So often you can actually remove those outliers and work with the data, and then it will be quite normal. So always check your data before you correlate them. So one of the things that I found, last week I was talking about the work for my thesis with my crazy coloured graphs over here. For me, that was quite hard to choose. Do I use Pearson's or Spearman? Because actually I have lots of different variables. Some of them are skewed, some of them are not. But actually for the outcome of the analysis, the data we were assuming, or rather we were trying to find data that was normally distributed. So part of that was, okay, I had to also describe the skewness in the histograms and understand, was it heavily skewed? And if it was, then that's going to make a relationship on that calculation, that's not less of a robust result for the correlation because one of the variables was skewed.
This picture is come from webcam?
Pardon?
This picture is generated by the webcam?
This picture's in my thesis. It's generated by processing. It's a type of software that you program to do what you want it to do with the data. But this is like literally each of these were programmed separately, and it's just grid mesh to build it together. So I'm going to describe a bit more detail of this because it should help understand.
Before making, for example, if I have lots of data,
Mm-hmm.
and I want to make some statistical analysis, I want to choose whether I'm going to use Pearson or even Spearman.
Mm-hmm.
Then the first step that I'm going to have to do is just scatter the data and then look at the distribution. Is it normally distributed or probably skewed?
Yeah.
I don't know, like Poisson, gamma, or anything else. And then suppose that the distribution is normal or Gaussian, then I can use the Pearson.
Yes.
So that's the first step.
Yes. So usually with any kind of statistical analysis, first step would be look at the data, describe the data. So we look at doing a histogram, for example, to look at the frequency, but we also can do a scatter plot to understand the correlation, just as an image. Yeah.
Probably doing like a QQ plot just to look at the
Yeah.
data is normally distributed or not, something like that.
Yeah.
And then if the data is normally distributed, then I can
Yeah.
choose Pearson.
Absolutely. Yeah. So you meet the assumptions, just like in the statistical tests, there's assumptions that you're supposed to meet to do that particular test for your data. If you meet them, absolutely do that test. And if you find there's more than one, then you have to look at which one makes more sense for your data. So correlations was something that was pretty core to my work, partly because I was looking at what's the relationship between us, residents, people who live in a country, and how much energy we use. And in particular, we were looking for patterns as to how can we create profiles of the population based on lots of different variables, so maybe your family size, the type of house that you live in, what kind of insulation you have, all these different variables would come together. But one of the major things before that was looking at how these two correlate, the different variables correlate with each other, and can we make some assumptions about the data. What I found was quite interesting with these, so this is a picture of England. These are little maps, and one is the increasing of gas consumption, and one's the increase of electricity consumption. These are all little boroughs about where people live. Yes, we could have done much detailed data, and I did do the analysis on much finer detailed data, but this is just to show an overview. So here, this is London. So we have much darker gas consumption over here, and actually relatively light in the centre of London. As we kind of go around the country, again, these green ones are showing the capital cities, the major cities. Up here we've got Manchester and Liverpool, big cities, and gas consumption is quite high. And weirdly, electricity consumption is quite low. These pink areas are the really remote kind of rural areas, and shows down in Cornwall, really low gas use and really a high electricity use. So that kind of thing, I was looking at the data. In my particular case, the geography of the data really was part of my work. Is there a geographical pattern in this data? Can we create geographical clusters and understand profiles of users based on where they live and what type of house they live in and stuff like this? So part of the next part of the analysis was then to look at this correlation. So looking at this correlation, you think doesn't really have any pattern at all. Potentially there's a small correlation here. Calculating the correlation coefficient this was Pearson's. So in here we've got -1 to 1. The colour represents how correlated it is, and it's actually relatively near 0. It's -0.3. Yeah, looking at the image, you think, okay, there's some clear correlations here, but what's interesting is they differ. So this is negative, positive, 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 and there's completely mixing up what that relationship is. So my work was then, okay, how can we look into detail of this? Can we explain it in more detail? So here we have the map. This is showing the correlation coefficient for the whole country. This is the one statistic, so it's -0.32. Then, because you use all your data when you calculate your correlation coefficient. But if we wanted to look for local patterns, we can use subsets of the data based on region and start to understand, is there local patterns? So we calculated it based on this kind of approach where you take your one variable, you look at how many neighbours you have, and take all the neighbours in that region to calculate the correlation coefficient. So if I take 100 neighbours from my little areas, then we start to see this pattern. So here we've got a really positive correlation going on between electricity and gas use in the city, London, and then everywhere else is relatively negative. I'll explain that in a second. As we decrease the number of neighbours, we start to get really quite a detailed pattern. We start to appear, this northern cities start to appear, and for the 25 neighbours, really, really clear that the centre of London is very different from the outer skirts, and we see this pretty interesting pattern of the country. This is getting to a really small sample size, so we have to be careful here. Same when we do experiments in general, you think about what's your sample size and how does that influence my data. But 50, 100 is pretty decent sample, and somewhere in the middle is probably more robust. But this was more of an experiment to see, can we see these patterns? One of the clear reasons why there's a clear pattern here is that gas pipelines don't get to the rural areas. There's no chance for them to get here. And right in the middle of the city, they also don't have many of the gas pipelines right in the centre of London. In the others, they do. But right underneath the centre of the old London, they don't. And most of the centre of London isn't actually living anyway. It's all offices. it's all work areas. So actually the calculation of the gas use probably isn't that much. But all around the outskirts, gas is very, very popular. And most of the time, if you don't have gas, you use electricity to heat your house. So hence, in the rural areas, there's a very negative correlation compared to the other. So this was one of the ways that we started to explore that data. That's where those little tiny maps come in. And then you see those clear kind of distinctions in the data. And one last thing. So this is our maps, shows it clearly, but we can also do the same thing in the scatter plot. So we can color those points based on what that value is at that particular location, and we can start to see a little bit of a difference in the data here. So I was saying earlier, we might be able to find some correlations if we subset the data. Here we can see those dark red ones. There's a linear correlation here, and there's another positive, and those dark blue ones, they're on kind of the opposite, so negative. So if we can subset the data, sometimes that helps us look and explore and really understand that correlation in more detail. But what's more interesting is, for my work, was, well, the global statistic doesn't actually give us anything about this pattern at all. You'd never see that pattern if you just looked at that one variable. So you have to sometimes explore that data in more context. Now you can see that my slides are far more picturesque than some of these ones.
So, but essentially, the local correlation is like finding the local minimum before actually reaching the global maximum, like an expectation maximum.
In terms of optimization, I suppose, yeah, I suppose could be classed in that way.
But the idea is just slicing from the whole data into subset of data to get a better picture.
Yeah. So we could, if we were looking at variables over time, for instance, we could slice the data by time. Is there time? So if we had, let's say 1 year's worth of data, but we break it down by month, can we see seasonal or monthly patterns in the data? Often, well, most of my work is usually how can we visualize that data? So how can we break it down into subsets? And then we start to see patterns, and then you test to see if there are some significant patterns or not. For me, I was more kind of interested in the sensitivity of those parameters. So if you change that number of neighbors, what happens to the result? Can we see something in more detail?
Numbers of n.
Yeah.
Is it the centroid or the numbers of I don't know, like the points or?
So in that sense, like we take the one location. So let's say we're in Caulfield. You take our little area and then you calculate the distance-based nearest neighbours. But there are plenty of ways to calculate it.
So that's actually in Caulfield, so actually 1 point, just like in your example.
Yeah.
London is 1 point, and then up here in Manchester.
Yeah.
And then it'll be another point. Is that what you're saying?
So each of those points on the scatter plot is one location on the map, one of those areas on the map. Yeah. And that's how geographical statistical data is usually mapped. You have like an area, but then sometimes you would call it, it's just a value for that area. You give the area a code or a name.
I mean, when you're saying, when you're using 25 as a number, 50 or 25.
Yeah, so that's the number around. So it's the number of neighbours around it. It's just kind of arbitrary, let's say, for this experiment, but we could have been much more robust in the way we calculated what's the most well, these are, you would never, if you were actually calculating it correctly, you would never say 150, 25. It was kind of like a, let's just do steps to see if we can see some patterns. But yeah, if I was doing this again, I'd probably look to see, can I calculate the best for that particular variable? But then that one variable might be different. Those two pairs might be different from another pair. And this was looking at hundreds of multivariate data. So it's quite difficult to kind of pick the perfect value. But yeah, so whether it's geography or it's species of plant or it's month of the year, there's one way to break up data to be able to look for individual patterns in the data. So regression analysis is kind of the next step here, that we're looking for that pattern. We're looking to see, is there a trend? So if we know how variables are related to one another, we can predict what happens next. As prediction might not be perfect. In general, forecasting is very not perfect, and then there's some uncertainty in that, but we can try and make a best guess. So when you did modelling, were you talking also about regression analysis with Peter? Were you looking at forecasting into the future? So this is probably one step before that, where it's the simplistic kind of way of calculating it. So regression of y and x and y, I usually set the other way around, looks to predict values for the dependent variable from a set of independent variables. So if you want to predict something over time, we have one is the set and the other variable is the one that's fluctuating. The most common form is linear regression, and it's also probably the most basic, so usually called basic linear regression. It assumes that the relationship can be described as a line, and it adds that noise around it. So earlier we saw some scatter plots that, okay, it's not a perfect line, but they're really roughly going up in a line, so we can calculate those and understand there's a slight noise around it. Then, yes, it's based on the correlation, and then it looks at the correlation squared, so that's the goodness of fit. How well does it fit to that line based on the data that's there. For example, here we have our scatter plot, we have our data points, and this is the regression line that's fitted here. And that's the kind of, when you tell your software, can you fit that line? It's looking to try and fit that based around the data and the errors associated with these other data points. So some of these are quite low, but even though it's not perfect in the middle, because it's taking that into account. So the formula is based on, here we're looking at time and growth. So we basically calculate these two values, and we get this R squared, which is our, what did I call it earlier? Yeah. Goodness of fit. So it's the goodness of fit value, and it helps us give that value here for our line. So that's what goodness of fit means. It's how good is the regression line? Is it measured? It's measured, yeah, with the R2, which is correlation squared. It measures the proportion of variance in the data that's explained by the model, the fitted model that it's trying to fit around, right? So your trend that you're associating, how well does that fit my data? So yeah, if R squared is 0, then the fitted explains none of the variance. It's very rarely going to be that, because otherwise it's quite unlikely to be that. And then if it's 1, it fits perfectly. So it's always between 0 and 1. Why is this model suspect? So we have our R squared value here with the 0.56. That's how well it fits this particular trend. Is this suspect? Do you think this is a good fit? Well, we don't have many data points, and these two are very out there compared to the other cluster here. So if we remove those two, we'd have a line much more like this. So we have to be careful of outliers, and this has a huge effect on our slope here. So if we actually remove those two, then we'd have a very different slope. So in theory, we should just calculate more, go and get more samples to see, well, how does our data fit? Are those two values actually outliers? Are they anomalies? Or did we miss some of those ones in the middle? So last week we were talking about Anscombe's quartet, how we have these 4 different data sets that are identical in their global statistics. So they have the same mean, they have the same n, they have the same correlation, and they have exactly the same curve line, regression line. So this is saying these 4 data sets are exactly the same. Well, obviously they're not. So we still have to be careful when we talk about regression, we talk about correlation, that we actually describe the data that we're looking at. We look at the data, we look for outliers, because here that's clearly not like this. It would be really like this if that data value was not there. Yeah, this one also quite a poor fit. It's not really a straight line. That one's pretty good. That first one, you go, okay, this is directly for the values. This one's probably okay, but you miss this outlier here. But that one does not associate anything with this curve, and this one in particular is a real problem. But yeah, this is a particularly interesting example where you really think, okay, I have to look at the data first. It's one of the things earlier you say, yes, create a scatter plot, describe the data, understand the data in a little bit more context, and then look to see what you can calculate. So when we're looking at these nonlinear relationships, for example, with this, you have this curve, we can fit nonlinear regression to it. So we have this flat curve in our data, in our trend line, and often is plotting the data on a log scale, and it helps to see this in a much more clearer light. Yeah, here. So you can see, well, here, if I use this and I plot it on a log scale, it's now going to be straight and it's linear. But yeah, so that's the next step. So you do linear regression is very, very basic, often doesn't fit most of our data because often we have this curve, so you can use nonlinear regression. And then we have multivariate regression, where we have lots of different data sets, and you have the input variables, the vector, and the output variable is a real number. And we're looking for the relationship between these two. And where is this S? Correlations, coefficient. Yeah. Interesting. Yeah, so it's most commonly found by minimizing this mean squared error, which is the sigma. And it also captures this noise, the missing data. So that's pretty important. Mean square error is the measure of how well a simple line describes the relationship between input, the dependent and independent variables. So it's calculated like this, MSE. Sounds like a dodgy disease. And yes, the average of the square errors. Avoid large error more than small errors. Okay, well, obviously outliers have a large effect, and outliers have a large effect on most of the regression analysis, so we generally have to be careful. There's loads of approaches to regression, and lots of different types of regression analysis. Look at your data, try and see what would be useful for that particular data set, and have a look at. If you're doing regression analysis, then definitely look at seeing what's the most sensible for you. Look at the assumptions that it needs, and you still basic linear regression is like one way, one approach, but often we need much more context.
Piecewise regression? Is this piecewise regression, like two regression lines? Because I can see the mean. It's shaped like.
So this is that where it has that line here. Segmented linear regression, so it's looking for segments in that line. So it'll come up in a minute, I think. There's, it looks for certain proportions of the graph to try and fit those lines into the data. For example, here. So here, for example, we have students' results versus effort. And some of the relationships are not exact, but they're in this region of the graph. So actually, it doesn't include these areas, and then you have this quite skewed results. But you can fit your curves into this proportion of the data that you're actually looking at, the proportion of the graph that you're looking at. So yeah, down here you haven't got any results, and down here that never really happens. So you have this kind of area of the graph that you're looking at. So if you have those two data sets compared to each other, similar to this, you can calculate the regression based on that one section of the scatter plot, let's call it, but it's that one section that basically you're subsetting your original possibilities, your outcomes, to this one area and saying it's going to be in this envelope, or in the previous region, everything's going to be in here, and where's it going to go? You almost remove the other things from your equation. That's just kind of the more complex analysis to really try and fit that line better to the data and the expected data in the future, so if we're forecasting much further into the future. So yeah, regression predicts one numerical variable from another. It must include the dependent variable in order to discover the regression function, but then can be used to predict future data from that original variable. Linear regression, simple linear regression fits a straight line, and it minimizes error, and yeah, there's lots of alternative approaches to look into detail. Yeah, the regression model can help understand the nature of a correlation, whereas the correlation analysis only assesses its strength, how those two correlate. So this area links very heavily with machine learning and classification and data mining even. So I'm sure you've done that before. So there's a lot of work linked to that and how they link to each other. There's loads of different examples of how to do this. We'll do some in the tutorial tomorrow, but yeah, R, for example, I found quite a lot of nice examples here. And yeah, obviously you can do something similar with Excel. But one of the things we have to be really careful, this is quite a popular thing to do. You do a scatter plot matrix, and you look at all your variables, you give them a trend line, but then you don't necessarily explain what that trend line's for. What is it actually trying to say? If you're going to add it in, then explain why you've added it. What is it showing? Really, what's the purpose of this line and the trend? There's no point in just adding it for kind of aesthetic purposes. You've got to kind of explain what it is and why you're using that. This is one of the kind of comics about the kind of regression, that actually everything can be fitted to a line. We've got to be really careful, explain what it is that you're doing and why you're doing that particular analysis, because otherwise we can predict anything, pretty much. But it gives quite a good overview of the types of lines we're looking at here. So the lowest line was the one on the previous slide with the matrix. That's one of the popular ones. It's a slight curvature in the line, tries to predict that line or curve. This is the one where we're looking at this area and how confident we are it's going to fit there. Yeah, lots of beautiful representations, but yeah, we just have to be careful about how we do it.
can you spend some time on the additional material about the polynomial regression?
Can do.
Yeah, I'm interested in that class.
Oh, you should take data science. They were talking about that.
I think, yeah, we'll have a look at that in a sec.
In the end of the lecture slides.
Yeah.
Can you look at the design now?
Right now,
Yeah. Okay. Talk about the
whether I know enough about it is another question. One sec, I don't like this. So this links back to one of the ones we were talking about earlier, the non-linear regression. It's very similar thing here, where we're inputting real values. What's the degree? This is the confidence interval, CI. So the area in which you're most confident that that regression line fits. And then here, the truth one, I'm not sure how it's calculated.
I want to know the order of the polynomial and the relationship. The relationship between the order of the polynomial and the fit line of the point.
The relationship of the
Order of the polynomial.
Yeah.
And how it fits the data.
I
If we get the more greater order,
Yeah.
can we get a better fit of the data?
Well, most of the time these kind of I'm going to call them complex regression analysis are looking to better fit that data. So yes, it's trying to fit that data in a much more robust way, and particularly when we can calculate these confidence levels to say this is how confident we are that that particular line fits this into near future. This will grow as we trying to go further into the next part of this. When we don't know the data, of course, it's going to get much wider, the confidence level. But I can't say too much more about binomial. I haven't done these for a while. But we can look at them in the tutorial. We can have a look in a bit more detail. The good thing about this class is it's not as complex as data science. You don't have to you don't have to kind of know it all. It's just not understand what those different aspects are doing and how you describe them, what statistics you're using, and for what reason, and justifying your approach.
Calculating using calculator. That's important because we have to do it by calculator.
Yeah. So in this class, it's like, well, yes, you and obviously the more you in your results, the more you describe it, the more. Certainly in week 6, for example, if you showed a really clear workings, then of course you get more marks. But yeah, for us, it's not so much about how to do it. It's more why would you do it, and is this sense suitable for my data, for my experiment, for my thesis? If so, great. We need to know more about it, and this is important for you. Then yeah, let's talk about it. But yeah, right now I'm jumping right outside of my comfort zone. But basically, it's fitting complex data to this line curve, right? So this is not just a straight linear if we put a line in here, that's not going to help us whatsoever. Yes, we'd have a line, but we need to have a curve in this sense. The data is clearly showing this kind of gradual increase and more of this like log representation. So probably didn't help very much, but yeah, we can talk about that tomorrow when you're in the tutorial. Tomorrow or Thursday? Should we skip the break? Because we don't need a break. There's just 2 of us. 3 of us.
Actually, I need to go.
Okay, you can have a break.
Sorry about that.
It's okay. Now I understand why you said, let's talk about it now. I was like, oh.
Actually, at least you have another student.
Yay! Well, we can try and rush through it and then. Thanks, see you.
See you tomorrow.
Mm-hmm.
Bye.
Yeah, that's okay.
Yeah, time series analysis is what it says on the tin. We're looking to order the sequence of data over time. We're looking to see what the trends are, what the patterns are, and how we can reproduce some of these using, for example, using regression. So loads of different types of time series analysis. I work particularly with energy consumption, but there's a very clear pattern over time and how energy use changes. So we can do quite some interesting data statistics there.
So essentially, time series is a series of data, each year by year or timely manner.
Yeah. Any time-dependent thing. So it could be seconds, could be minutes, could be years, could be.
So essentially, that's time series then.
Yes. Anything that's related over time, and in particular, time series analysis is looking to do short-term or long-term forecasting. So, for example, if you're looking at weather, that's clearly over time. There's a trend that we have in Melbourne for having lots of seasons in one day, but there is clearly forecasting that happens with that. So they look for 2 variables or many variables that relate to each other and can predict what's going to happen in the future. So not just, weather's a very typical one, but things like currency, fluctuations, all that kind of stuff. It's all time series analysis. And yeah, we aim to identify components over time, and we break the data into zones or phases. We look for filtering. We try and see these different components. So time series often has, like the previous slide, these quite clear patterns. So it has like peaks and troughs, and that's what we're trying to kind of replicate to do our time series analysis. So these breakpoints, they're valid when a given process applies. Yeah, so so basically, we identify breakpoints in our data to understand these peaks and troughs. So, for example, like if there's a storm going to happen, or there's a very periodic thing that happens over time, and one of the things that we can do is the cumulative sum of square. Cumulative sum of square, it's called. I don't like this. It's a simple way to locate these breakpoints. You calculate it using the progressive sum of values along a time series, and you exaggerate these trends in mean or variance, and it's the changing of the slope, and it's like the how the mean changes, and the change of the variance. So, for example, we look here at these spikes, that, for example, is the website use has hits per day over the different days. Certain often this happens when you have a website, some media has gone out and everyone hits the website at a particular same time, and then it drops again and then hits a high again. Yeah, so this calculation looks for these peaks and changes over time. So as our gradient increases here, we can see that that's a change in angle. That's indicating that we've got a change in our original data. So we can do this for mean and variance. We can indicate what's happening over time in our graph. It's basically a visual representation to understand what the data is trying to say and how do we indicate that there's a clear change in the data or that pattern. Yeah, for example, this is pollen preserved in the lake sediment, and it reveals forest changes in the past. So it's applied this custom cumulative sum of square applies to the data, and we can see this changing over time. So we have these little points here where we can see that's where this data is changing, and the real indications of there's some distinct changes in the data. So then we look to filter the data, and so we highlight these patterns and the series, and for example, let's look at the next slide even better. If we have our original data, we can see this is the moving average, and we can have the difference. We can calculate the difference over the short-term variations over time. So if you look back over here, so the difference filter highlights these pulses and shift in their variance, and the auto-regression process looks at the model's short-term process with memory. Yeah. So we're basically looking how can we present this original data, really detect those changes and look for the difference. So another example here where we've got temperature changes over 1,000 years. We look for those moving averages, so we can reveal this cycle, and we can also reveal a long-term trend by calculating the cumulative sum squared. So time series analysis is statistical interpretation of time series data. We use it for forecasting, projecting, understanding temporal processes, and we have to identify the trend, the cycle, and the kind of noise around that data to really predict that. And we build this composite model based on those three things.
So essentially, when we're talking about, for example, if we aggregate the data, for example, we have the temperature data over 100 years, for example, and then but each year we have each month, for example, and then how about we just aggregate the data, like, for example, we have like 12 months in 1 year, so suppose that we have 1,200 months in one century, for example.
Yeah.
And then how about we just, aggregate each year from 12 months, we just sum and then we average them into one data, and then we just have only 100 points of data instead of having 1,200.
Yeah, so we often do that as well. So, but usually it depends on how precise your predictions you want to. Do you want to forecast daily changes or monthly, yearly changes, or do you want to forecast decade changes? So if you're, of course, the more aggregated the data, once you aggregate the data, you lose some of those details. but sometimes those details are not necessary for our prediction, so it totally depends on what we're looking to try and predict.
So essentially we can do both of them, like just trying to find doing the custom, so there's cumulative of sum, or just trying to look at and see the difference within them.
Yeah, so I would, personally it depends on what your outcome is, and really do you have that fine detailed data, in which case then actually sometimes you try both. So you look for, well, is there a yearly pattern? Can I predict what it would be for coming years? Or maybe you will also look for more fine, robust kind of example. But I think, yeah, that example where you've got thousands of years worth of data, you're never going to be looking at daily data changes, because actually that's not really, it doesn't really make sense. Right? So in that sense, yes, you're looking more at the yearly changes over time. So we'd be predicting what's that pattern, the forecast for each year, and then how does that change for the next 1,000 years, let's say. So it depends on your research question. So we look components of time series analysis. We look for trends, the changes in the mean or variance. The stationary series have no trends. Well, that's because they're stationary. Function of time or of another series. Sure, okay. Most of the time, though, because we're talking time series, we're looking at time. But this happens a lot, these cycles. In my old job, we used to look, and that's the one about the hits on the website. Very much it was a seasonal thing. People in fact, it was a price comparison company for electricity or gas. So people would change their supplier just before it gets to winter, because suddenly the prices have gone up and they're going to heat their homes. So it was definitely very seasonal. And there were certain other periods that we could clearly distinguish between what the data, and just looking at the data, there was clear kind of differences between if it was raining, weekend and weekday, and time of day as to when people would be hitting that website. So there was clear cycles, and would have been, they probably did it, interesting to see if they'd forecasted that, well, they could predict when the servers would be really heavy and how they can mitigate that. Sometimes that there would be a website would crash because so many people were hitting it at the same time. Yeah, white noise. This is the fluctuations in our data. We always get fluctuations in the data. There will always be some kind of errors depending on what kind of data it is, but usually there will be some kind of fluctuations in the data, particularly when we're looking at, well, even the website hits, there will always be one that's a crazy, crazy amount, and you're just like, that doesn't meet our understanding of it, and sometimes you can almost remove that as white noise. Yeah, and so you use these more descriptive representations of the data. So yeah, that's components of time series. We look for cycles, we incorporate noise, we try and combine them together to predict what the future will hold. Here's an example. This is methane concentrations over years. Can't even read the numbers. That's how poor this site. I think that's a 9. 90, 80, 82, 84, 86, 88, 90. So if we look at this particular trend, we've got, looking at the cycles, we can see that we can convert this particular data into this line and looking for this trend, and it explains 86% of the variance. But if we fit a curve based on seasonality, we can look at the sine function and then we have this nice curve, but it only explains, well, rather it explains 80% of the seasonal variation in the data. So then together, we can combine the two, so we incorporate the trend and the season, and we get a much better representation of the model. So that's kind of, we look to try and improve models by combining the different variations. And then, of course, you still need to make sure that you're careful with knowing the errors and the limitations of each of those before you say that it's the best at the result for your work. But yeah, that's how we kind of calculate them. Then we look at the residuals. Is the observed data minus the corresponding values of the model. So did the residuals show clear cycles or trends? And the frequency of the residuals should be this approximate normal distribution.
We always assume that all the residuals will be Gaussian, unlike normally distributed.
I
have to always assume that way.
Do we have to always assume? I think the assumption is that they are, but we should check that they are.
Sometimes in toy examples, in toy problems, always, we have to have like this kind of assumption that all the epsilon must be normally distributed. But I still wonder why do we have to assume that way? I'm like, why? And then what would that be if not the case, for example? That's always come to my mind. I've never been able to ask that kind of questions. But regardless, that's okay.
With this, not like we assume normal distribution to basically judge whether or justify that we've used the relative model or the relative statistical test or whatever. And if the results aren't normal, then perhaps we've done it wrong. So actually, it's worth checking. Potentially they might not be, but I think you'd have that kind of understanding of having a look back and seeing whether it actually calculated correctly. Most of the time, it's just an additional check. So yeah, that's long-term forecasting, where we build this model from trends and cycles and noise, and we look at the cumulative sums to identify those breaks. We fit a trend to that data between the breaks, and then we fit those cycles to the residuals, and then we assess the errors and test that model. So what's the advantage of it? Of course, it helps towards the understanding of that process. We can make forecasts in advance. It's robust with the random variations, but long-term forecasts are often not very accurate they're less accurate than the short-term forecasts. And they also fail if the process changes. So on that note, short-term forecasting is we build a model from previous values of a series. We use auto-regression to predict, and we correlate the data. So we correlate the time series with past values of the same series and all time series. We create a regression model of that series against past values. And then in this sense, we don't have to understand that process. It's more accurate at that small detail level, or the small short-term, of course, at forecasting level. The further we go ahead, it's less accurate. We only need to calculate one time unit ahead, and it's very sensitive to random outliers, and it fails if the process changes again. Maybe So yeah, if, for example, with this one, if we go too far ahead, what will happen? Well, we'll end up probably with a curve like this rather than going up.
So the green line is the auto-regression?
The green line is, this is the prediction for the short term. Well, that's the regression line. So if we continue with that line, would it go like this? Probably. When actually we probably want to increase slowly over time, so it would take the next next loop over time, and then calculate that quite well, and it'd be quite accurate. But the more we further ahead we go, then that line doesn't quite fit it anymore. So there's various issues with forecasting. We need to test the model. We need to test it, to build it and test it. With forecasting, we use training data to do that. I mean, you've done modeling already, and you use your one data set, but then you want to try and test it with other data sets to see how well that fits. It's quite difficult often that we trying to find another data set that is the same as the one you're looking at. So you can take subsets of your data. So you train one period of time and see how well it forecasts. You add your next time series in to see is that forecast what the expected results. And then we need to need an indication of accuracy. So we use this residual errors to estimate these confidence levels. Another thing we can do is this cross-correlogram, where correlation between these different time series have time lags, and we increase. So it's a calculation. It calculates a correlation between variables for all possible time lags, and it's a way to kind of compare if our time series meets the needs of our data. For each time lag, the lineup series make scatter plot R squared value fast. So if we, for example, the next plot, it's actually probably easier. So we do this, we line up the two series with an offset. We plot points on a scatter plot. We calculate the correlation R for the scatter plot. We repeat steps 2 and 3 for all the different time delays. And then we do this cross-correlogram plot to show the values of R against decay.
So essentially we just mean shifting to the right one to the left side. Is that what it says?
Shifting the right onto the...
I saw like minus 25, plus 25. Okay, line up T2 shaders, 80 with an offset for that line. That's kind of cool.
So if we look at the next slide, it's probably easier. So we can do a serial version of these, where we look at a series compared to itself, and systematic of zero lag, so only. Well, I think we should look at these tomorrow, because the slides don't really help. Correlation between different time series often have time lags. Increase in stream flow lags behind rainfall in the mountains, right? Okay. We can calculate the correlation between our variables for our different time lags. So we can say, right, is it 25, let's say. We do like almost subsets of the data, and then for each time lag, we create lineup series, make a scatter plot, we calculate the R squared value, and then we can graph that against time. So that should be this. So then we'll have lots of R values that we can calculate across time. So it just so happens that here we'll have 25 to 20. So that's here to here. When there's a 0.1, there's one unit. We calculate it for every single unit from minus 25, minus 24. all the way up to plus 25. And then we have an R value for each of our data values, and we can see how well it fits.
Yeah, essentially just and then try to figure out which one the best one.
Yeah.
That's good.
Yeah, so it's quite a useful post-analysis to understand, does it fit our time series analysis.
Yeah, because in data science, we learn so many things to start to do, but we lack of the foundation. That's why I'm more interested in this idea instead of having because we've had that enough in other
Yeah. I think, some of these things that I was trying to avoid going into too much detail, and it's almost that kind of trying to meet the needs of everyone in the class when everyone's doing very different theses or very different kind of analysis, and then what's classes has everyone else done before. So maybe some people are doing data science, but other people aren't. So it's almost, that's why there's no one here. It's the basic background of some of those statistics and why we do them. But yeah, there's so much so you saw with my example of correlation, yes, it is one value, but there's so much more detail in that. So I was looking into local data variables and changes, and how on earth do we explain them to the user, and can we calculate them, and what are the sensitivity of those parameter changes. But of course, sensitivity analysis can be done with all these different types of statistics. If we tweak one little area, if we change our sample size, if we look at a longer time series, how do we explain that data and then explain it in our results? So this looks like it's just a series of them to understand the general pattern over time. So this is for short-term forecasting. Hopefully that's still useful. I think there's more that we can do. There's certainly, I think we do one of these in the tutorial, so we'll have a look into that. And then that's pretty much it.
Yeah, that's what I'm saying. Me, we as data science students, we lack a foundation, the statistical foundation. Because we're more into that, more machine learning stuff.
Yeah.
Supervise and unsupervised, and other than grading stats, running forest, but not necessarily looking at the foundation level. Because sometimes when, I remember exactly when Professor one time said that you don't always look at the more sophisticated level when you perform your analysis, but you have to look at the, the simplest one. For example, do the regression analysis first, instead of having random forest or even decision trees, random forest, gradient descent, but do regression first. Sometimes the most fundamental ones, it's going to be saving you a lot of time.
Yeah. So my thesis was, so that was a tiny part of it, but that analysis was almost a grounding for, I was doing clustering analysis and trying to build profiles of the customers based on all this data, but then going one step back was kind of like, well, actually, if someone else was doing this, so big thing about research is you're trying to make it reproducible. So making sure that if someone else was doing the same thing, how would they understand which variables I used and why? And that became more of, actually, it's more interesting from my work, it became much more interesting to kind of explore that. How do we choose the variables and really detect, there's interesting patterns in that data that I want to include in the clustering, and geography was a big part of that. So if there's a geographical variation in the data that shows some clear correlations between those two variables, that's really interesting for this particular work. but just looking at those raw numbers, correlation, would never have even seen that. So yeah, I almost did the same thing. I kind of took 2 steps back to kind of go, but why would you do that?
Yeah.
And actually, let's, before we go ahead and do all this nice profiling and actually do some nice clustering and classification, there's various steps which are not very clear. And to do them in a better, more consistent way was more important for our work at the end than to do that more complex.
More sophisticated.
I mean, it's more sophisticated, but actually the final result, you still have to justify it. So if you justify it and then you look at it and you're like, yeah, but could someone else do this? Do I explain it in the right way to, or have I given all my code, and if someone else runs it, will they get the same result?
Yeah.
And every time I did it, I was like, someone else doing the same thing would not choose that same variable, probably not. So, yeah, that was for me quite an interesting question, because yeah, you take those step backs to say, why would I do this? Which is, I mean, it's data science in general. Like you can use some very complex algorithms, but if you want to make reproducible research that someone else can then use to continue that research, you have to be really clear about why you did it. And if someone questions what you did and why, then that's also kind of like, oh yeah, why did I do that?
Yeah, sometimes, I found like people of journals wrote by, very, very smart people. They tend to be really tedious in a way that they wrote it deliberately complex so that the readers and like newbie readers couldn't understand what are they, and that's just really annoying. One of them, I used one of the journals, and I had to see my co-supervisor just ask him just how to explain him what this was actually about. So that's why. And he just told me that sometimes the researchers often did that. They just make things complicated, overcomplicated things, in order just to make sure that the readers would presumably, making assumption that they are very, very smart people. I mean, I don't. Well, they're obviously smart, but how could they even do that? And
yeah, I think it makes a big difference from the kind of background that you come from and the kind of discipline, or the field that you've come from. So I read, my thesis I had to read from engineering through to sociology, behavioural science, loads of different types of journal articles across the board of why do we consume energy in different ways. And it was not just from people and that kind of thing, but also looking at clustering and trying to create profiles, but then also understanding some of the most complex things from the engineering. And reading them was, across the board, very different. Some were very simple, really easy to understand.
Yeah.
Some were straight over your head, and you have to read it a few times to get there. And there's this really nice example that you might like. Have you seen this?
No.
So this is, I work in visualization, and one of the things I suppose we do with visualization is try and tell a story about the data. So this one, it's not mine, but I really like this because they're trying to explain what machine learning is. So it's, I can put the link up, but it goes on for quite a while, but it explains, I have these different data sets. This is 2 different home elevation data. So this is whether a home in San Francisco or in New York. So it's looking, is that home in San Francisco or not? And it's talking about elevation. and can the computer learn about this, and does it put them in the right places? So then we have our little scatter plot here based on FIT and price. So I think there was the two features, extremely expensive per square foot, and this is the scatter plot to indicate it, and we have these different boundaries to associate price and meters. And then we've got all these different variables going into our analysis to help it, and then we've got these different patterns in those ones. And this decision tree kind of looks to put them into the relative areas. So then it looks at the distribution, histogram, frequency of the data, and the color obviously represents the city. Oops, I missed. Oops, sorry. If a home's elevation is above a certain number, then the home is probably in San Francisco. So in machine learning, these statements are called forks, and they split the data into two different branches. So it's nicely presented, nicely explained. It's called a split point if the values between the branches, the homes to the left of that point get characterized into one, and the ones on the other side go to the other. And then picking a split point is quite has trade-offs. So obviously we could falsely classify one or the other. So here it's talking about these are false positives, and we have our best split here, and we can calculate these. So the algorithm calculates these, it bases on the subsets of the data, it repeats them, and it tries to train the data. And generally, we have our little tree. So here we have our three different data sets, or three different variables, and we have to we look at how well it predicts. And then it keeps going down and down. It builds this nice little tree based on how well it's predicting the data. You can continue to add branches until the tree's prediction is 100%. So at the end of each branch, the homes are purely in San Francisco or purely in New York. So it basically is, it's learning on this data, and it uses each of these to make decisions and says, okay, this is elevation is the first thing, then price per square meter, then year built, etc., etc. Eventually we end up with all our training data being perfectly classified into our leaf nodes, and we can then make predictions. So it's a very beautiful.
I wish I had this.
It's a very beautiful representation. So here it's training the data. Everything nicely fits in, keeps going, and fits into the relatively areas of the tree. But of course, then you have to use your actual data. It's seen this data before, and then you can test it with your other data. And we can see here we've got some false positives appearing. But generally it's pretty good, but it's not perfect. So then these are due to overfitting, and then you have to perfect your model.
Very nice.
So yeah, so to me this is the kind of thing that we well, not necessarily this particular way, but this particular representation, looking at visually creating something that will help people understand a complex process. Usually, not necessarily looking at trying to understand statistics, but usually it's we have multivariate data, and then how can we describe it in a much more intuitive way. But this, some really nice ways of doing that. Anyway, R2D3 it's called.
I got it.
Yeah. There's always good examples. So, how's your presentation for next week?
Presentation, we have a guide, probably, yeah, I've got some to do tomorrow, so
I'm expecting something like this, R2D3, like this. Yeah, you're going to be as beautiful.
I know, it's not going to be like that. I've got things, well, like, you know, we have to write our thesis, and also I'm going to have to build my artifact for the reading units, or the thesis part, so lots of work to do.
Yeah, tell me about it.
All right.
Thanks.
See you tomorrow.
Yeah.
Thank you.
Bye.